Now moving on to our lightning talks. Our first lightning talk is from Carlos Siquedo. I hope I'm saying your name. All right. Oh. There you are. Watch your step.
Yeah. I'll time myself also. Good. Okay, good. Let me see if I can change this so I can do the, okay. Anyway, so good morning. So I'm Carlos Caicedo Bastidas from Syracuse University, part of the Cosmos NRDZ team, which has members from several institutions. And I think Ivan from Rutgers and Gil from Columbia are around in case you want to talk to us. So yeah, our project is spectrum sharing via consumption models and telemetry, prototyping and field testing in an urban FCC innovation zone. But basically, as all the NERDS teams, we're trying to build a zone management system, as was explained before by John Chapin. You know, we're trying to kind of understand the spectrum use within a given radiodynamic zone, protect that use, and understand how that experiments or the spectrum used in the zone could impact neighboring areas, or how neighboring areas could also impact what's being done in the zone. That's kind of the high level of it. So our zone is in the New York City under an FCC innovation zone under which the Cosmos platform for advanced wireless research operates. We have the a nice thing in the sense that there's also a NOAA center located within the zone, and so we're collaborating with that center in order to do some experiments related to protecting passive devices within a radiodynamic zone. The high-level architecture for zone management system is shown there. I'll explain some more details as we go along, but key items for our zone management system are capture of telemetry data, sensor data, and then converting that data and other inputs into a standardized way of representing spectrum use based on an IEEE standard called spectrum consumption models, which I'll also expand on in a minute. So again, just to give context, you know, Cosmos and NOAA Center living close by. We have equipment and facilities that allow us to be close to each other and experiment rather tightly with devices that are both in Cosmos and in the NOAA Center. So as part of the infrastructure that's within the NOAA Center, there are microwave radiometers, there are passive satellite receivers, and weather radars that we can experiment against. For the purposes of what I'm going to show today, we're concentrated on the experiments for protecting a passive microwave radiometer, mostly focusing on the 27 to 29 gigahertz band, which overlaps with the band of operation of the radiometer. It also overlaps with the frequencies in which Cosmos is allowed to conduct experiments as a platform for advanced wireless research and FCC innovation zone, and also overlaps with a spectrum being used for 5G communications with operators like Verizon, which are close by. So, but we're planning to do experiments with other devices that are in the NOAA Center, but for now it's just the radiometer. So a microwave radiometer is a very sensible device which captures the thermally emitted radio wave emissions of the atmosphere. I think that's a nice way of putting it. And with that information, it basically can give you humidity and water vapor content information, which is useful in weather forecasting and weather monitoring. That's kind of the high level of it. Moving forward, we're trying to protect this kind of device because, again, it is very sensible. So, as one of the key items in our protection mechanisms and the operation as a zone management system, we're using spectrum consumption models as standardized by IEEE 1900.502. Full disclosure, I'm one of the IEEE standards officers who helped standardize, build the standard, and so, but my points of view about the standard are my own today and not those of IEEE, I have to say that. So SEMs are basically a data model that helps in defining a concrete specification of how what are the boundaries of spectrum used by any transmitter or receiver device or a collection of devices. And so it is based on a few pieces of information, which we call constructs. Not all of them are necessary to represent the boundaries of spectrum use of a device, but being a standardized machine-readable format that clearly defines how a device uses spectrum, we can build algorithms on top of it and machine learning on top of it, and it basically creates the logic for our zone management system. So then, as we're trying to protect devices within the zone management system, we need to build spectrum consumption models for each of them. So like it says there, to protect the radiometer, we need to build an SEM for it. The minimum constraints that we need, the minimum pieces of information that we need are for that SEM, for that device, are listed there. So we conducted a few set of experiments to capture some of that information, basically by generating on purpose interference to the device. So the way we generate interference to the device in order to understand clearly how it's capturing RF energy is by using a phase array antenna module, that portable one that operates at 28 gigahertz, that's available in Cosmos and has been developed with the Cosmos team in collaboration with IBM, if I ever recall. And so that's what we're using to generate our interference at 28 gigahertz. We needed to characterize that device, experimental device. We need to characterize it very well so that we know what we're getting out of it when a particular configuration is given to it. So now that we know what we are emitting in terms of interference and how we can adjust that power and how it gets adjusted, what value comes out of the device, then we can actually go to the rooftop and start, of the NOAA Center and start doing experiments with it. So this is just a snapshot of one of the experiment sets. So the idea was to kind of understand what is the maximum tolerable interference of the radiometer. So by that we mean the amount of interference after which there is a notable distortion on the measurements generated by the device, right? And that's a key piece of information that goes into a construct in the SEM named the underlay mask. So then we kind of identify, there are powers that kind of distort. Oh, you don't see my mouse, but there are powers that clearly distort the measurements. But then after we reduce the interference power, we found a region of acceptable interference where we are still emitting interference, but it does not produce a distortion to the measurements. We verified this with the weather guys in NOAA, and they found those measurements acceptable. So long story short, we identified the limit of maximum acceptable interference threshold for the device, and now that gets fed into the SEM. So it's minus 86.66 dBm at a 10 megahertz reference bandwidth, just if you're curious. Another thing that we did is to fully characterize the antenna pattern, the receiving antenna pattern of the device. This was just so that we're thorough. There was enough information in the manual from the manufacturer to do some characterization of the antenna receiving pattern, but not at some angles, just at the main angles, in which when the device is pointing towards the sky. So just to be thorough, we did some measurements to capture that pattern. And so we feed this into an SEM, which then can we feed these measurements into NSM, and then our logic for spectrum deconfliction and spectrum management can use the information in the SEM to actually protect the device if we have the SEMs of potential interference within the zone. So where's this all going? So we're heavily automating the process of taking in measurements and generating SEMs from it. We're exposing APIs that hopefully will help other people and or students feed information quickly into our zone management system. We finished the elaboration of our SEM generation API, trying to make it easy for, again, students and others to feed measurements into our system and generate SEMs into them and populate those SEMs into our database and do spectrum deconfliction. We're also building ways to capture information from other tools developed by other collaborators so that that information from those tools can also help us build SEMs for our zone. Okay, so that's where we are.
Thank you.
Thank you.
So, thank you. In the interest of staying on time, we'll have to save questions for the coffee break. I guess I forgot to mention that as you get closer to your time, you'll see me sort of starting inching closer to you and your presentation.
I saw that. It was effective.
It was effective. Okay. Next up, we have Greg Helborg from Caltech. I thought you were on here. I saw you.
Yeah, it's this one. Thank you. Good morning, and thank you, Chris and John, for having me here. So my name is Greg Helborg. I am a scientist and spectrum manager at Caltech, and I'm going to talk to you about our new project, which is the Deep Synoptic Array, the DSA 2000. So what this telescope is, it is a very novel type of telescope. What we want to do is to provide the radio astronomy community with a telescope that is both very sensitive and also very fast at imaging the sky. And it is a survey instrument. So basically, we're going to survey the total accessible sky over 5 years with 16 epochs. So really what we want to do, as you can see here, this is a kind of a plot in which all the next generation radio telescopes are put in continuum sensitivity versus survey speed. And we really want to be on the top right of this graph. So how do we do that? Well, the telescope is very big. It's 2,000 antennas. Each antenna is a 5-meter dish, dual polarized receiver. The telescope will cover 700 megahertz to 2 gigahertz, and will have an incredible sensitivity down to 1 microjansky. We expect the detection error survey of 1 billion radio sources, which is about 2 orders of magnitude compared to current surveys. So as I said, 2,000 antennas, which will be located in a valley in Nevada. The total footprint of the telescope will span 15 kilometers by 19 kilometers. It covers 700 megahertz to 2 gigahertz. And it is a radio camera. So what that means is to maximize sensitivity, we'll have, well, a lot of collecting area, right? 2,000 antennas, a wide bandwidth, also integration times of about an hour per pointing over 5 years. Each pointing in the sky is about 3.3 arc seconds. It is low cost front end, which means that we have no cryo cooling. We achieve 25 Kelvin of system temperature with the room temperature receivers, and we're also designing a radio camera. So, for those of you who are not familiar with radio astronomy, and I gather there's a lot of people in this situation here, usually in radio astronomy we collect data for a while, and then we send the data to the astronomers who will eventually produce images. What we want to do, and that's how we achieve very fast survey speed, is to produce images in real time through a completely streamlined pipeline. So as you can see, the left part of the pipeline shows just data capture, so ADC and channelization, and everything goes then into very strong GPU servers that are responsible for the production of the correlation between all the antennas, the calibration and R5 flagging, and all the other types of processing that we do in astronomy. Now, this is pretty serious business because there's no, space for any mistake when you do alpha mitigation, because everything is real time. We don't store the data, we store the science ready data. Now, the this all works, of course, if there's no issue with RFI, and there's going to be issues with RFI. This is where I spend most of my time, or I've spent most of my time in the past few years. So as I said, the telescope covers 700 megahertz to 2 gigahertz, which is, I like to split it into 3 bands, the lower 300 megahertz and the upper 300 megahertz, which is mostly allocated to terrestrial services, and particularly cellular services. And the mid-band, which is mostly allocated to aeronautical and satellite services. So really, when we want to find a site that minimizes the interference, we focus on the lower and upper band, because that's what's terrestrial, right? Wherever you are in Nevada, you will pretty much have the same occupancy of the spectrum in the mid-band, but it's the lower and the upper part of the spectrum that is going to change. So because most of the allocation in those bands are cellular, the first thing that we did is to look at the distribution of the cell towers across the US. And when you look at this, it's pretty obvious that Nevada is a very good candidate for installing such a radio telescope, simply because there is a much lower population density, which obviously correlates with a much lower cellular towers density. So to survey Nevada, of course, well, it's a big state, so it's a lot of work to just travel around and monitor the spectrum. So what we did first is to identify all the candidate sites. Candidate site meaning all the valleys that are big enough to host the telescope in the first place, and that have access to power distribution, fiber distribution. And then we ran some RF propagation simulations to understand how the cell towers will propagate in the valleys, in the potential sites. So this is an example of our actually main candidate site, the Spring Valley, in the middle. So it's kind of represented by those 4 stars in the middle. And 2 cell towers are the closest cell towers, and see how the propagation of those cell towers happens in the valley. Once we've identified the top valleys, for us, we actually went on site. Now, what you see here is a map of the Spring Valley, the same valley as before. And in blue, it's the theoretical footprint of the telescope. So each blue dot is an antenna, 2,000 points. And the red stars correspond to spectrum monitoring points, and the green points are the cell towers. So we've basically measured spectra in each of those spots. And I don't know if those spectra mean anything to you, but having spent a lot of time looking at many spectra in this frequency range, I can tell you that these are uniquely quiet. Now, on the top left, you have the spectrum that corresponds to the site number 1, which is outside the telescope footprint, and kind of in a direct line of sight with the southern cell tower, which explains why you have pretty strong transmissions in the lower part and the upper part of the band, which you would not find in the other spectra, so the other monitoring point, just because the mountain chain kind of offers good protection, good RF protection. And with all that, well, we came up with this table that is very important to us. It's a comprehensive list of all the sources of interference that we'll have to deal with our telescope. So most of them, of course, are satellites and aeronautical as well, which are the ones that we kind of not are able to avoid. But we also find T-Mobile, AT&T, Verizon, and we're in contact with them. We try to find mitigation solutions on their side before working on mitigation on our side. The most important column in this table is the mitigation part, the middle column, that explains what is the most optimum technique for mitigating that one particular RFI, and how much data can we potentially recover if we implement this mitigation technique. And we'll achieve a pretty good recovery of band. We estimate that at most 17.08% of the band will be lost due to RFI, which is within the margin of the project. So that's good news, and that's it for me.
Thank you. Our next presentation, clear out a couple of these, is Elliot Eichen from the University of Colorado at Boulder, talking about spectrum sharing between wireless communications systems and Earth sensing satellites. And if you haven't provided your slides to me, either through the Google Drive or on a USB drive or something like that, you have an opportunity to do that during the coffee break and during the lunch.
Where's slideshow?
Right there.
I can't see without my glasses.
I'll get it. Maybe. There we are.
Okay, thanks very much. I'm Elliot Eichen from the University of Colorado, and I'm going to be talking about sharing millimeter wave spectrum between the very sensitive radiometers that are used to measure water vapor and temperature in the atmosphere, and sharing that spectrum with 5G and 6G networks. So you've already heard from the first two speakers. First, you've heard about how sensitive the radiometers are, and these radiometers are orders of magnitude more sensitive than what you would think of as a commercial receiver in a base station or in a cell phone. And that's often overlooked by people like me who worked most of their lives in the communication industry. These are just incredibly, enormously sensitive devices with long integration times. And you've also heard about the interference from satellites, interference from transmitting satellites above the Earth that interfere with radio astronomy observations on the ground. So you can think about this form, real-time geofencing of EESS radiometers, as the inverse problem to the radio astronomy problem. In this case, the receivers, the very sensitive receivers, are on satellites that are quickly orbiting the Earth every 100 minutes. So they pass over, they make a full pass around the Earth every 90 or 100 minutes. And the transmitters are on the ground. So in some sense, it's the opposite of that problem. It's also very, you can also think about it as a cousin or a relationship to CBRS deployments. Because it's a geofencing type of mechanism, and you can use the same types of zone management systems or spectrum access systems to geofence the location of those measurements and basically prevent interference. So how does this work? Well, very quickly, it works because the area that the radiometer looks at over time is a very small area. And it moves very quickly, so that the time over which it overlaps with a transmitter tends to be someplace between 10, 20 milliseconds up to a couple of hundred milliseconds, depending upon the type of radiometer. And if you were to add up take all of the 21 satellites that currently measure, for example, at 23.8 gigahertz, and they pass twice a day, typically 2 or 3 times a day over any given point, and you were to look at the time that occupancy happens, it tends to be a little bit less than 1% of the total time during a day. And so what that means is that 99% of the time, that satellite is not looking where the transmitter is, and so there is no interference. So if you're able to geofence over that period of time when the overlap actually happens, you're able to prevent interference from happening at the satellite, and then you can return the rest of the spectrum in principle for communication purposes. So there are lots of reasons why this is a very good way to do this. It's a software mechanism instead of a hardware mechanism, so it's extremely flexible, and it allows you to run networks that are in some ways hotter and provide better performance than you would from when comparing to the type of ITU regulations that we currently have today. At the same time, it can provide better interference protection to the satellites. So it's sort of a tastes great, less filling kind of idea. So one of the things that we've done, and we've talked about this for a while, one of the things that we've done over the last year is to look at how accurately we can predict the time at which you have to basically do something with your network. And so cross-track scanners are probably the most important type of radiometer, and these are which the radiometer points at the Earth and scans orthogonally to the direction of the satellite. And so we know where the satellite is very precisely, but what we don't know is where it's pointing at any given point in time. We don't know the phase of the satellite. So it turns out that these radiometers are like clocks. They're incredibly good pieces of engineering, particularly for something that is motorized and it's running around really fast. And so if you look at the data that is downloaded from the satellite a few hours before the satellite actually passes over a given location, you can recover the phase. It's almost like a clock recovery type of idea. And because these things are so well engineered, you're talking about a variance a couple of hours later that is in the microseconds range. And so the net of all of that, without going through all of this stuff in great gory detail, is that we can measure to less than a pixel. We can predict where the satellite will be looking to less than a pixel. And that allows us a lot of opportunity to provide this type of geofencing. There are lots of reasons why this is a better way to do things than the way we currently do it. I don't propose that this is something that will replace the ITU's methodology, but I do propose that it's something that can augment the ITU's way of doing things. And I don't have time to go through all of this stuff. I'm happy to talk about it, but there are tons of reasons why this is a good thing, a better thing, and a cheaper thing to do than putting things in hardware, where once it's in hardware, it's really hard to change stuff. So I want to give you sort of the punchline and the summary behind this. Passive measurements are really important. They're important for both weather forecasting and for climate models. I think that's sometimes overlooked, and that's how I got interested in this particular subject. And so this is the do no harm part of it. Whatever you do, do no harm. The second part of this is that it does work. It provides better protection for these measurements, and at the same time, it allows you to run your networks hotter and better. And a great example of this is Qualcomm's high-powered modems that they have defined for, God, I'm blanking on it. They're defined for the fixed wireless access. That's the word I'm looking for. They haven't been able to deploy them because they can't they can't reach the interference spec that's required. And so this becomes really important, by the way, for the last mile. I spent the majority of my career working on the last mile, and it's really expensive. Whether you do it in fiber or you do it even in coax, which isn't very good, that leaf is really, really expensive. And so I think this is the use case, the compelling use case for 5G. Everybody's talking about the fact that millimeter wave spectrum for 5G hasn't had much in the way of adoption. And as my colleague Liliana has pointed out to me, it's because it's the wrong use case. The mobile use case is not the use case. I think fixed wireless is the use case. Okay, so it works, it's better. That's the tastes great and less filling. Who cares about NR2? Well, I think certainly the Department of Defense and NASA and NOAA care about it because they're all very sensitive to getting good weather measurements. The climate community really cares about it because climate modeling is really important. And I think that the communications community will come back to it. I know they're coming back to it in certain places, and I think it's important in order to do that. So what we've done as part of NERDS is been to define build a system that can do this type of protection. We're making APIs publicly available for that. There's a demo next door where you can come see it. And so what happens there is you give us a lat longe, a date, and a frequency range, and we will return to you all the times that you need to do something to your network. And I haven't really talked about it, but just turning off the network is not really the ideal way to do it. There's tons of flexibility to add time of day and traffic statistics, moving traffic around based on class of service. There are a whole bunch of things that you can do to make it happen. And the last time, give me 1 second, the last time before you kick me off is that our future work really depends on providing incentives so that the community, the ecosystem of this stuff really will go forward. And there's a piece of the pie here for pretty much everyone in this stuff. And just the last slide, come see our demo, it's next door. Thank you.
All right, thanks, Elliot. And our last lightning talk before we hit the coffee break is from Kevin Gifford, also at the University of Colorado Boulder, talking about his open source satellite orbit prediction processor. Let me find your PowerPoint slides.
Send full screen, okay. Thank you guys. Thank you, Chris, and thanks, John, for inviting me here. So I'm really going to talk about how to help protect radio astronomy from the satellite perspective and knowing where the satellites are. I've got some open source software that I want to talk to you about. On Monday, I had given a deeper dive into how the satellite orbit prediction processor, which I call SOPP instead of SOP, but I gave a deeper dive of what was going on there. We really honestly have a bigger problem, or a problem that I need the community to help me solve. So let me go forward with this. And I want to say thanks to David DeBoer, who I work with at Hat Creek Radio Astronomy Observatory, and Andy Clegg and Mark Gibson, who are heavily involved with the Wind Forum and have given me some ideas about the problems they've had with CBRS missing data and with AFC missing data. So I've kind of coalesced all this together and am looking to make a call to arms to the community to help solve this problem. So David DeBoer, and I'm sure all you radio astronomers, you know, when I got into this 4 years ago, I thought this was a great statement, right? It was illuminating to me. I didn't know about this. The satellites are the great equalizers, and of course you guys all know that. I have a couple of pictures. I was looking for some icons last night and got a little jiggy with finding those and thought that was pretty cute. But, you know, I don't need to set the basis here. You know, whether it is active terrestrial emitters affecting RA, as Greg was talking about, or whether it is satellite emitters overhead affecting RA. The problem is radio astronomy is getting their scientific observations compromised. And that really was the problem I was looking at. Both the terrestrial emitters and the satellite emitters, this focuses on the satellite emitters. One thing that's interesting, I don't know if you guys have seen this before, N2YO.com. I don't use it for anything. Well, I use it for, but I love this top where typically there are 2,000 satellites over the top of you at any place in the world. That's just kind of an intuition, right? And of course they're moving in and out, but knowing that number just tells you the problem that radio astronomy potentially could have. At HCRO, it's not just one telescope like the Green Bank telescope. There's 42 6.1 meter dishes. That gives you the opportunity to really kind of turn it into a sensor array. If you want to do some satellite spotting of multiple satellites or multiple frequencies or cover the sky, there's just some interesting experiments you can do with an array there. And of course, Greg's going to have an array of 2,000 dishes. So the project goal, really, is to connect radio astronomy, observatory schedules, right? You typically know what you're doing to some level of degree, and their satellite ephemeris to a portal-based kind of an informing incumbent capability, right? And then you can geofence or protect the RA systems via cloud-based sharing systems, and this really is 100% similar to AFC, 6 gigahertz AFC, to CBRS SAS, and to a zone management system such as at the University of Utah, which is envisioned to control an RDZ. So ephemeris is quite simply a table giving, you know, when the satellite is going to come over you at a specific time. And so the project that I'm working on with David DeBoer and others is to include this proof of concept and protect HCRO and the satellite, the 42 dishes that are there, from satellite interference coming over the top. And this is all informed by SOPP. So I wanted to quickly give a call out to SOPP as open source. I highlighted the URL there. We really have advanced this. Everyone, the leaders of the RA facilities, have your workers and your grad students download this and pound on it. We really need more use cases. We've evolved this. I am working on this with Frank Lynn and then Chris Dupree at NRAO as well, but we would like to expand the community, get the user feedback, make sure that the software is providing value, and would just look for general improvements. So really quickly, you guys, this is not a detailed overview, but it's a Python library, and really what you do is you input your observation input parameter. You know where you're at, your geolocations, you know your antenna characteristics, you know the celestial object you're pointing at, you know your time window, you know the satellites coming by. Let's put it all together and figure out when the satellites are going to interfere with the RA facilities. And so I'm not going to go into too much more detail than that, other than there's really, speaking John's emphasis on professional software development, 100% agree with. And so I had a grad student working on this for a couple of years, and now I've transitioned it to a professional software developer, and you can imagine great learning for the grad student, but it needs to be taken to the next level. I want the community to help me take it to another level here. So there's some details here, but essentially there are two primary classes or functionalities that you can do a bunch of work with, and that is figure out if satellites are crossing the main beam and then get satellites above the horizon. And then you can do additional activities if they're above the horizon and pointing a different way or not over the main beam bore site of the telescope. You can make some calculations and predictions, inferences in that way. So really quickly, this is actually Zera, right, which is the Russian module on ISS. We're just showing it pass a couple of times here. We know this orbit. We know the max altitude at the exact time. You know this from the satellite ephemerae, and you know this for everything that's defined. These are very accurate, and they get periodically updated. Sorry, I hit the... So the next thing we do is, and this is what motivated us to start this SOPP, was to figure out when satellites were crossing the main beam if we could give radio astronomers the better window to do their observations. That was the initial motivation, but when we started writing this, we figured out, well, we could easily do satellite spotting, which has got some interesting, maybe DoD implications as well. But here is what I want to get to, because I got one more minute. The problem is that there is a lot of data that's not available. Okay, we've got the satellite ephemerae. We typically know the satellites. The red in the middle is showing all the satellites. If there's gaps there, if it's yellow, we don't know the downlink frequency or the frequency bandwidth. And so here is the last 40 seconds. I'm pretty well on time. This is what I want to do, and bluntly, this is at the advice of Mark Gibson and Andy Clegg, who have gone through this. You've got a bunch of sources, right, of all this data, but it's not readily available by an API, right? And so lots of times you've got to dig into the actual filings and scrape that data. That is just, what needs to be avoided. So here are all the sources. I like this idea of a third-party data curator that maintains the integrity. Right? So you pull all this data together, you package it up, and you've got a bunch of users, such as SOPP. You've got Andy's famous Spectrum Wiki, which is being reinvigorated. You've got other users that could utilize that data to protect their systems. And that was 0815, Chris. Thanks, everyone. I gotta grab this. Thank you.
Sure, no worries. So amazingly enough, we are on schedule, or maybe